Now we consider the exact solution in case of a flow on an infinite plate. So we imagine that there is an infinite plate ranging from, let's say, minus infinity to plus infinity, or for long distance, and somewhere we can choose the origin, and the whole flow is taking place along this plate. So no motion in the vertical or in any other direction. So this is a very simple geometry of a flow field, and therefore we expect simple things from the solutions also that we see. So it's one of the simplest form, and since the whole motion is taking place therefore in the x direction, therefore only the velocity component in the x direction is non-zero, but the velocity components in y and z directions respectively, that is the velocity component v and the velocity component w, are both zero. And the continuity equation will also be simply du by dx, the partial derivatives, and since v and w are zero, so those partial derivatives vanish. So the only non-zero derivative that will have some contribution, that may or may not have contribution, will be this one. And of course, for some motion to take place, this has to be non-zero. If u is zero, then we will conclude that there is no motion at all. So, since the geometry, we have taken the flow field situation that the fluid flow is taking place only in the x direction. So this part is non-zero, and if we integrate it, it is obvious that if we integrate it, let's say, in a two-dimensional situation, then the velocity u will be dependent only on, possibly on, y. Why? Because du by dx is already zero. So from this it follows that u does not depend on x. It follows from here. So it has to depend on the other variable, and that will be, let us say, by some value of u of y that is unknown at the moment. This is one conclusion that we have derived from continuity equation. Then we come to the other parts, the xy components of Navier-Stokes equation, and from this, since du by dx is zero, the partial derivative with respect to x, therefore the partial derivative only of y, d2u by dy2, will be zero. All other terms will vanish, and pressure P will be some constant. So using no slip condition, because at the boundary, if there is a fluid flow taking place close to this plate, and let's say there is origin here, and this is x, this is minus x, so all the motion taking place more or less in this direction. So at this place where x is 0, y is 0, if y is in the direction, then due to viscosity there is no slip condition prevailing. Meaning, because of viscosity, the fluid is stick to the wall, the plate that is infinite in nature, and since it is stick to the wall because of viscosity, there is no horizontal or vertical motion right at the boundary, right where x is 0. As we will go away from the plate, there will be some motion, but close to it, right on the surface, there is nothing. And then, of course, by taking the integrations of different values that we realized, we will have the wall shear, that is shear at the wall, to be denoted by tau. Remember that by tau we denote the shear forces, and W here is only denoting that we are calculating it at the wall. So this will be equal to mu times partial derivative of u by uy at y equal to 0. So this will bring us to the right on top of the plate. And therefore, this will give us, the result will be that u will be equal to tau w by mu into y. And this, it follows from here that u is proportional to y. If tau w, the stress or the shear at the wall, and the kinematic viscosity, the coefficient of viscosity mu is constant. So for a given fluid, if there are not multiple number of fluids present there, if there is only one fluid, then it will have a constant kind of viscosity, coefficient of viscosity. So this part is constant, and if we introduce the sign of proportionality, we see that the velocity component is linearly proportional to y. That means that the velocity u will be kind of proportional to the value of y in the y direction. So that is the result that we derived, and that will prevail for this kind of geometrical specification.